Welcome to the craziest talk I have ever delivered. This is my cancelled APS March meeting talk, which I was asked to make the information publicly available through an online medium because the American Physical Society meeting in March 2020 was cancelled due to the coronavirus. So what I would have actually shared with you in LA this month or last week in Denver is some recent work that I have been doing with collaborators from the University of California, Davis, Oxford, Griffith University in Australia, Imperial, NIST, and ICOCI, among others. And the question we were actually very much interested in this work was, can you develop a preference for describing events as occurring in one particular temporal order directly from observational data, without necessarily knowing anything about how these events were generated? And if we could find such a preference, then where would it come from? So to launch us off and establish the basic premise for this talk, I have here a video of a guy kicking down a door in reverse time. And when I first saw this movie, I was very confused, in the sense that I had absolutely no idea what was going on. And this puzzlement sort of captures the idea that events are often a lot more difficult to rationalize and comprehend when they're presented to us in one particular temporal order versus, say, in the reverse causal direction. So a hallmark example being watching a movie in reverse time makes it a lot more difficult to understand and comprehend than watching it in forward time. Or something like one of Christopher Nolan's films, such as the movie Memento, which is iconic for having its scenes scrambled out of chronological order, can be quite an intellectual exercise to follow and comprehend, because it's really only right at the end of the movie, when you can take the disparate scenes and sort of piece them together into a coherent narrative, that things begin to actually make sense. And at this stage, you're tracking a lot of information about the prior plot line to do this reconstruction. So this begs the question, are events generically easier to understand and comprehend when they're presented to us in one particular causal order over the other, say? In the sense that, do I need to record and retain less information about the sequence of preceding events in order to make an accurate prediction about what's going to happen next if I encounter these events in direction left to right in the data string versus in direction right to left? And this turns out to be true. It's a very well-known phenomenon in the context of complexity science, which is called causal asymmetry or causal irreversibility in the literature. And what it says is that if Bob wants to take a sample of what's happened so far in the past and use it to make a statistically accurate prediction about what's going to transpire in the future, and his counterpart here, Alice, wants to take a sample of what happens in the future, use it to make a statistically accurate rate prediction about what may have transpired so far in the past, then in general, Bob's task can be significantly easier than Alice's, in the sense that you can execute it with a far smaller memory system or a much smaller hard drive space in the context of digital simulation. So to concretize these ideas, I have a much more physically accessible example here. This is a box containing a single fair coin, and at each time step we perturb this box, causing the coin to flip with some probability p. At the end of the time step, the box announces the outcome of the coin flip by emitting a 0 if the coin lands in tails and a 1 if the coin lands in heads. And in doing so, it generates strings of 1s and 0s, which look a little bit like this. However, what I'm going to do is I'm going to post-process this data by taking the first 0 in each consecutive block of zeros and replacing it by a 2. And intuitively, this is a relatively procedurally simple thing to do if we are doing it from right to left in the data string. In the sense that I simply need to scan the data string from right to left, and whenever I see a 1 transition into a 0, I say, okay, this is the first 0 in a consecutive block of zeros. I'm going to replace it by a 2. However, if I try to execute the same post-processing task from left to right in the data string, then it appears like it might be slightly more complex or a more complicated task to do. And since I'm now scanning from right to left, I'm required to replace the last 0 in a consecutive string of zeros with a 2. So I'm scanning along, I'm asking, is this the last 0 in a consecutive block of zeros? And to establish this point, I really need to look one time step into the future to decide whether the preceding symbol is going to be a 1 or a 0. And then come back and modify my last output conditionally if the next symbol turns out to be a 1. So at the outset, this seems like this actually might be a data string which is more difficult to generate and explain in one particular causal order over the other, say. And indeed, this intuition is completely capable of being formalized in the context of computational mechanics, which is a sub-branch of the discipline of complexity science. In particular, computational mechanics deals with the question, what is the minimal internal structure a system must have in order to be capable of exhibiting certain observed behavior? So the premise here is that you might be dealing with a very complex environmental system, something like a weather system or a traffic network, or maybe crowd dynamics. And you really have no hope of modeling and understanding the system from first principles. Instead, what computational mechanics allows you to do is to take a data string representing observed behavior of this process over sequential moments in time. And in particular, you can take the past events in this data string, some x past, map it into an internal state, s of x past, of some machine or model, where the state is in general a function of what's happened so far in the past, such that afterwards, systematic application of a physical process on this memory system at each future time step allows you to generate a sequence of future events which is statistically indistinguishable from the behavior of the real-life physical system itself. And what this means is that if I were to take my model on my machine and I encase it inside a black box, and analogously I took my real-life physical system and encased it inside a second black box, then operationally there'd be no way to tell these two black boxes apart. Their behavior would be entirely statistically indistinguishable. And in particular, framework of computational mechanics is very clever. What it does is it gives you the minimal memory such machine capable of executing this task. So the way it does this is that it directly discards any information contained in the past which is not relevant to predicting the future. So it takes any two pasts which lead to statistically indistinguishable future behavior and identifies them with a single internal state of memory of the machine known as a causal state. And in doing so, it induces an equivalence relation of partitioning on the space of all pasts, in which any two pasts which lead to statistically indistinguishable futures become identified with a single equivalence class, the causal state of the past. And there's a lot of equations which will be available through the slides hosted on the American Physical Society's website. So I'm sorry, not everything's going to resolve properly because my camera's resolution isn't great. However, if you are interested, please look at the APS's website. This entire meeting is now going online. So all the resources will be there. So this compression on the past actually loses us no information about the future. And in fact, if we take an appropriately initialized machine, initialized in the state SX past that proxies the past, then we can always recover a statistically accurate sample of what may transpire into the future simply by iterating through internal transitions on the memory subsystem, which are governed by a collection of hopping probabilities, which again, you're going to have to look at the APS's website for the details of. And the significance of this construction is that it's actually the machine which hosts the minimal internal entropy or the smallest memory system capable of executing this task of replicating the future behavior. And in particular, the internal entropy of the system is quantified by the Shannon entropy of the distribution over causal states. It therefore captures the minimum amount of information you must retain about the past in order to be capable of predicting what will happen in the future with statistical accuracy. And because of this, it's become a very widely adopted quantifier of structure and complexity in the complex systems literature. It's been applied to systems such as traffic networks, neural spike trains, stock markets, stripping faucets, pseudo-random number generators, biological systems. There's quite a large category of different physical processes whose complexity has been analyzed through this particular measure, which is known as the statistical complexity of the process. So if we return to our simple coin process from earlier in this talk, we now directly have the tools to construct the memory optimal devices for replicating these statistics in forward and in reverse time. In particular, what we find is that the memory optimal model for generating this particular process in forward time is a two-state edge-emitting hidden Markov model. And in particular, this machine based on this model must always retain one bit of information about the past in order to make a statistically accurate prediction about what's going to happen in the future. This is irrespective of the coin's probability of flipping P. However, if we try to replicate the same behavior in reverse time from right to left in this data string, then it turns out that we would need a three-state automaton. And in particular, this three-state edge-emitting hidden Markov model always retains, in general, greater than one bit of information about the future in order to make a statistically accurate retrodiction about what may have transpired in the past. So what happens is that these constructions are provably memory optimal. So this gap here actually tells us something very fundamental about this process. It inherently takes more information to replicate these statistics in reverse time than it does to generate them in forward time. And because of this, this phenomenon of causal asymmetry in this process has actually been speculated to be the origin of a barbed arrow of time in stochastic data series. What we should note actually before we move on though is that we were able to replicate the statistics or predict the future using a simple two-state automaton. So it was possible to execute this task using a classical memory system or substrate of dimension 2. However, if you wanted to actually generate the same process in reverse time, then the minimum internal memory subsystem we needed to actually host a simulator was had at least three distinguishable configurations. And therefore, in reverse time, we needed a memory substrate with at least 3 levels classically to replicate this process. So there's also an asymmetry, a causal asymmetry, in the amount of dimensionality of the physical system required to actually execute these tasks when going in forward time versus when going in reverse time. So this would be apparently the end of this talk, because these techniques are provably memory optimal. However, a very intriguing possibility actually arises when we consider the possibility of modeling and manipulating information to generate these statistics quantum mechanically. And you can get an inkling of the idea behind this from the double slit experiment, which is a notorious experiment in quantum information theory and quantum mechanics, where a single photon, upon approaching a partition with a pair of slits, simultaneously passes through both slits at the same time in quantum superposition. So the wave function of this single photon evolves into quantum superposition over all possible future trajectories in a simple system. And it's true when you have multiple partitions concatenated too. So this begs the question, can we harness this effect, this proclivity of the photon, to evolve into a superposition over all possible future paths to generate superpositions over all possible futures of arbitrary given stochastic processes? And this is exactly what we have an algorithm for doing. We have an algorithm which takes the past and encodes it inside a quantum state of a quantum system. And then this quantum device comes along and it interacts with blank tape. And in doing so, it can induce the tape to form a superposition over all possible futures of the stochastic process. So you get a quantum superposition over all future predictions. What's more, the really significant thing about this construction is that it actually generically stores less information than the statistical complexity to do this task. So it uses less memory than its optimal classical counterpart for predicting the future. The algorithm is extremely simple conceptually. All we do is we take stochastic transition dynamics governing the behavior of the internal memory of our optimal classical model, and we encode them into a unitary quantum circuit. And we just need to tile this unitary quantum circuit at each time step in order to generate a superposition over all possible futures of the process. What happens then is if we make a computational basis measurement on the states in the superposition, then the output of the simulator will collapse into one particular sample of what may transpire next. So in doing so, what happens is that we recover the exact same statistical predictions as our optimal classical model. So this quantum device fulfills all the tenets we required out of a model in executing the exact same task, while storing less information than the provable classical minimum. So it beats its optimal classical counterparts. However, if we're paying attention, this collapse of the superposition over all futures into the computational basis state actually destroys a lot of information about the future, which is encoded in the output of the quantum simulator. In fact, all the information about the future statistics, which is encoded into the quantum coherences of the quantum superposition over all futures, is destroyed in this collapse. And actually that means that we've thrown away and discarded a lot of the power of our quantum simulator. So our quantum simulator could do something which our classical could not. So we've managed to force it to replicate the behavior of the classical machine, but in doing so, actually we've failed to harness a lot of the power that this new device would have offered us. So if we return to our simple coin process there, then it turns out that in 4-time we can replicate the statistics by encoding the two states of my optimal classical model inside these quantum states here. Afterwards, simply repeatedly executing this unitary quantum circuit at each time step will cause the quantum device output a superposition over all possible futures of this coin process. Of course, computational basis measurements then requires a statistically accurate prediction about what's going to transpire next. If we wish to replicate the same statistics in reverse time, then all we need to do is take the 3 internal states of our optimal classical retrodictive model for retrodicting the past and identify them with these 3 quantum states here. Again, application of another very simple unitary quantum circuit at each time step allows us to generate superpositions over all possible pasts in this process, and therefore we can also sample statistically accurate retrodiction of what may have happened in the past. So remember, this was a process which exhibited a barbed arrow of time classically, in the sense that while it only required 1 bit of information to replicate the process in 4-time, irrespective of the coin's probability of flipping, in general it required far more than 1 bit to execute the same task in reverse time. However, what we find is that quantum mechanically, the internal states of the optimal the quantum predictive model for predicting the future and the internal states of the quantum retrodictive model for retrodicting the past both lie within a single qubit. Now this means that quantum mechanically it will always take at most 1 bit of information to model this process in either temporal order. What's more, we're already seeing a departure from the classical case here. Classically, we required at least a 2-level classical system as a memory substrate to execute this task in 4-time, but a minimum of 3 classical levels was required to execute the same task in reverse time. However, quantum mechanically, a single 2-level quantum system known as a qubit will suffice to generate you the statistics in either causal order. And indeed, this is enough to completely lift the causal asymmetry at the quantum level, in the sense that these 2 models for predicting the future quantum mechanically and retrodicting the past quantum mechanically have the exact same internal entropy or exact same memory cost of executing. And in both cases is far lower than its optimal classical counterpart. And actually, we can prove that these are the memory optimal quantum constructions, which is to say that if you took any other quantum system and started repeatedly applying a measurement operator at each time step to extract the statistics of the process, then your quantum system would have a higher memory complexity or a higher internal entropy than the constructions shown on the previous 2 slides. Which means that this is a process where the barbed arrow of time at the quantum level simply vanishes. So at the quantum level, it has the same amount of information to explain or replicate the statistics in either causal order. Nevertheless, what's happening is that a barbed arrow time is emerging when we restrict ourselves to using a classical causal explanation for these events. So when we restrict ourselves to imputing a classical causal model to explain the data, then this asymmetry between retrodiction and prediction emerges. But it wasn't there at the quantum level, which is really actually quite interesting, as it suggests one of the reasons for this observed phenomena, this barbed arrow of time, is restricting ourselves to only using classical causal explanations for events. What happens for arbitrary stochastic processes? Well, here we can think about causal asymmetry as a memory overhead penalty, a cost you must pay when insisting on replicating the statistics in a particular adversarial temporal order. And this penalty, this gap, is quite generic. Most stochastic processes exhibit this effect. Most of them exhibit causal asymmetry. And what we can show, though, is that for an arbitrary stochastic process, well, quantum mechanics can always mitigate this overhead penalty, in the sense that quantum mechanics can remove it such that your quantum model running a prefixed causal order always stores less information than its optimal classical counterpart running in either causal direction, or when minimized over the best possible causal direction for modeling the process. So quantum mechanics is always more efficient than classical, no matter which causal order you allow the classical to be executed in. And this is a completely general result, so we can apply it to arbitrary stochastic processes, including cases where the causal asymmetry grows without bounds as we amp up a parameter in the process. So these are examples of processes where the classical memory cost of actually replicating the statistics in one particular causal order is finite and bounded. It can be quite small. However, if we wish to replicate the process in the reverse causal direction, then the memory cost actually diverges towards infinity as we ramp up a parameter in the process. However, our results basically show that quantum mechanically, you always pay a smaller memory cost than the classical model running in the optimal temporal order, irrespective of what direction you decide to actually model the statistics in quantum mechanically. And this leads directly to scaling advantages where the quantum memory cost of executing the task is small, finite, and bounded, but the classical memory cost of executing the same task diverges towards infinity as we ramp up a parameter in the process. And we have a lot of examples of this now. It's also quite a generic phenomenon. And I've actually taken an example directly from some colleagues, Thomas Elliott and Miller Gu, which really nicely actually shows the advantage, which is diverging towards infinity, that you receive from executing the quantum model over its optimal classical counterpart. These are the results all apply in terms of dimensionality as well, which is to say that we also have a collapse in causal asymmetry and dimensionality of the memory substrate required to execute these tasks in forward and reverse time. We also have infinite scaling advantages in the dimensionality of the memory substrate required to model something quantum mechanically versus with its optimal classical counterpart. And we were able to actually realize and demonstrate these results experimentally with colleagues at Griffith University in Australia. And this was a really exciting development. What it allowed us to do was directly construct a quantum device which could see a superposition over all possible futures. We did this in two contexts. In the first context, we modeled the process in this talk in reverse time, actually, constructing a quantum superposition over all possible pasts one step into the past. And therefore, we were able to confirm experimentally the collapse of causal asymmetry at the quantum level in this process. In the second experiment over here, we were actually able to build a superposition over all possible futures for 3 time steps into the future of another very simple stochastic process. And this is quite a cool experiment because we didn't measure the outputs of all possible futures produced by this simulator in the computational basis. Instead, what we did was we took 2 such quantum simulators, each simulating a slightly different stochastic process. We produced superpositions over all possible futures in both processes at the same time, and then we interfered the 2 outputs, superposition states, quantum mechanically, And this allows us to recover a measure of the rate at which the futures of these two processes diverged through quantum interference. So the takeaway message from this talk very much is that the boundary of time and causal asymmetry in stochastic processes could in part be due to our proclivity to restrict ourselves to classical causal explanations, in the sense that the message about where the arrow is, what direction it's pointing, and if it exists at the quantum level is not nearly as clear as it is in the classical case. We are based in the National University of Singapore and also in Nanyang Technological University in Singapore. So if you've liked some of the ideas in this talk, please do come look us up. We're very sorry to have missed you at the March meeting. However, we also have collaborators all over the world. We've been very lucky in the community who's been working on this topic. We have collaborators, in fact, who may be closer to you if you're currently feeling travel restrictions. These include collaborators at Griffith University in Australia, such as Jeff Pride, Howard Weizmann, Nora Tischler, collaborators at Oxford University in Blackberry Ridgerell's group, collaborators in University of California, Davis, and James Crutchfield's group, as well as collaborators in Imperial College and also in NIST, and collaborators in ICOCI in Vienna as well. So if you're interested, the slides for this talk will be hosted through the American Physical Society's website, and all the details about the people who have played key roles will actually be directly available from the slides. But also there is a lot of very interesting and exciting theoretical developments in this framework, which you may not be covered directly here in this talk, and the people responsible for them, you can find them by searching through Google Scholar, because there's quite a nice body of work on Google Scholar about this now too. So I'm very sorry to have missed you. It was a pleasure to be able to give this presentation today, and I hope you all stay safe.